Hello all. Uh, Good evening, everyone. So today we'll be starting uh, our new topic, which is basically it is week 4. So in today's lecture, we will be discussing about the weighted graphs, which is single source shortest path algorithm, dijkstra algorithm, and its analysis. We'll be seeing its time complexity and all. And if a graph is with negative edge, then we can see that how can we find the shortest path from source to the destination using bellman algorithm, and all pair shortest path and minimum cost spanning trees. We will also see to find the minimum cost spanning tree. We will be using Prim's and kruskal algorithm. So this is our agenda for this week today. So if we start from, so like the last few weeks, we will be trying to solve some questions this week also. So let's start with our first question. So our first question is basically to find out the number of spanning tree with total number of spanning tree possible with 4 fully connected graphs. So first let me introduce some basic concept about the graphs. So a graph is a simple graph which has some nodes and which has some edges. Okay. So this is the definition of the simple graph. So uh, this is basically simple graph. This is called node and this is called edge. Okay. And if a graph has two nodes and or maybe multiple nodes, and if it has a node direction like this, so this is called undirected graph. This is called directed graph, and this graph is called undirected graph. Okay. So, and what is in this question, you can see that this is a number of spanning tree possible in a 4 node fully connected graph. So it is saying that the graph has 4 nodes. Okay. And fully connected means all the nodes are connected to, each node is connected to each other node in the graph, and so in like this. Okay. So here you can see that the nodes is basically there are 4 nodes, and number of edges is basically 6 edges possible. Okay. Now from here you have to find the number of spanning tree possible. Okay. So what is the basically definition of spanning tree? So if I so spanning tree is basically, if I have a graph. Okay. If I have a graph like this. Okay. Then I can find out that with 3 edges, I can cover all the vertices. Okay. So this will be a spanning tree of this graph. Okay. So this is basically spanning tree. Okay. So you so this is obvious that multiple spanning tree will be possible. Okay. So like this. Okay. So how many spanning tree will we can find out from this graph? So this is the question basically. So please remind a simple formula. If we have n number of vertices, okay, in a complete graph, then number of spanning tree possible is equal to n to the power n minus 2. Okay, so this is the formula. So here we have vertices, number of vertices is equal to 4. So how many spanning tree will be possible? It will be 4 to the power 4 minus 2 is equal to 4 square is equal to 16. So 16 will be the answer. Okay, so you can use a simple example also, like so option D, the 16 is the correct answer. Okay, so remember this formula only. Okay, this is the important one. Okay, so if you see a simple example of maybe three node, simple example with 3 node. So according to our formula, how many spanning tree will be possible? If n is equal to n minus 2, it is 3 to the power 3 minus 2 is equal to 3. So you check manually that if it is possible or not. So this is a graph. Okay, because why this is a graph? Because every node is connected. Okay, and this is a fully connected graph. So all nodes are connected to all other nodes using a edge. Okay, so there is no other edge possible in this graph. Okay, so how can you, so what will be the spanning tree here? So spanning tree will be this one. So this could not be a spanning tree, because here you can see that if there is only one edge, so all vertices are not covered. Like from this node you can go to here but not here. Okay, so this is not a spanning tree. So what is the basically spanning tree? If you have a tree, okay, so you can go from every node to every other node. Okay, so this 1 2 3, these are basically three spanning tree possible from this graph. Okay, so this is a graph and this is a tree. Okay, so this is the simple example with 3 nodes. So if anyone has any question, like if anyone has any doubt, you can raise your hand or type in the chat box. Okay, I think this is clear to you. Okay, so our question was about the spanning tree, number of spanning tree possible for fully connected graph. So fully connected graph means all vertices are connected to all other vertices of that graph using some edges. Okay, so this is the issue. So what we have done here, we have taken a simple graph with 3 nodes which is fully connected. So you can see that 3 nodes and 3 edges. Okay, so I have tried to find out number of spanning tree using this graph. So you can see that no other spanning tree will be possible for this graph. Okay, so you can see here I have find out the formula. Using the formula also it is coming that 3 spanning tree is possible from this graph. Okay, now the question is, find out the minimum number of spanning tree possible for a graph. Okay, so how can we do it? So now let me number this. So if I give you a graph like this, okay, so this is a graph. So you can see that this is not a fully connected graph. Okay, so now how can we found the minimum number of spanning tree possible for this graph? So for fully connected graph I have the formula. Okay, so this was the formula for fully connected graph, but this graph we have now is not a fully connected graph. So how can we find the minimum number of spanning tree possible? So there is a theorem called Kirchhoff theorem. We will be seeing that soon. So can you please can anyone write in the chat box that what will be the answer after calculating? So what we will do, so let's see how to solve this problem, this kind of problem. Okay, so first what we have to do, if you have a given, if you are given a graph, so you can see that this graph is of 4 nodes. So b is equal to 4. Okay, there are 4 nodes. Okay, so given a graph, construct the adjacency matrix. If there are k vertices, matrix will be of size k by k. So I have k is equal to 4 or b is equal to 4. Okay, so I have to write its adjacency matrix. So 1 2 3 4 1 2 3 4. So in adjacency matrix, what do we write basically? So if there is an edge between v1 to v2, then put 1, otherwise put 0. So you can see that from 1 to 1, is there an edge? No. So there is no self loop like this one. There is no self loop. Okay, so we can write the diagonal element as 0 everywhere. Okay, fine. Now if there is a edge between 1 to 2, no. So put 0. If there is there any edge between 1 to 3? Yes, there is a edge between 1 to 3, this one. So put 1. There is a edge between 1 to 4, this one. So put 1. Like this. Okay. So from 1 to 2 there is no, 2 to 1, 2 to 1 there is no edge. So that's why I have written 0. Okay. Then 1 1. Okay. 1 1 1. Okay. Okay, so this is the scenario. Okay, then what you have to do? So what you have to do now, this is the adjacency matrix, nothing but adjacency matrix. Fine. This is adjacency matrix. Okay, so what you have to do now, if there is the diagonal are zeros, so these are the diagonal elements, you know the diagonal elements, so these are the diagonal elements. If diagonal elements are 0, replace them with degree of the nodes. Okay, so how can we replace this? So you can see that the degree of 1, what is the degree? Number of outgoing or incoming edges. So you can see it is 2. Okay, so 1 degree is 2. Degree of number 1 node number 1 is 2. So what is the degree of node number 2? Degree of node 2 is also 2. What is the degree of node number 3? This is 1 2 3. So write 3 here. So degree of node number 4, 1 2 3, right? 3 here. Fine, no problem. Now what you have to do, if non-diagonal ones, replace it with -1, and non-diagonal zeros will be remain unchanged. Okay, so what will be there? So non-diagonal 1 will be replaced with -1. So here it will, you have minus 1 for this one. Now for this one you will have minus 1 again. Okay, now for this one it will be minus 1 and minus 1. Okay, minus 1 minus 1 minus 1 minus 1 minus 1 minus 1. Okay, and others will be 0 as these zeros are unchanged. Okay, so what we will do next? So what is the degree basically? So degree is basically number of adjacent edge that are incident or to any node is called the degree. Okay, so what will be the number of spanning tree will be minimum number of spanning tree will be possible from this graph. So it will be the cofactor of any element. Okay, so what is the cofactor? So how can you find the cofactor of any element? So cofactor of any element you can find out by omitting the row and column of the element and then find out the determinant. So what we will do, if you want to find out the cofactor of this element 2, how we will find out? So what you have to do? So you have to, if you want to find out the cofactor of these two, so you have to find out the determinant of this. Okay, because you will be omitting this its row and its column. Okay, then you will be finding out the determinant. Got it? So what you will write here? So you will be writing 2 0 minus 1 minus 1 0 2 minus 1 minus 1 minus 1 minus 1 3 minus 1 minus 1 minus 1 minus 1 3. So I am just copying it. Okay, now I will be finding the cofactor of this node. So I will be finding out this determinant. So what will be determinant of this matrix? So determinant of 2 minus 1 minus 1 minus 1 3 minus 1 minus 1 minus 1 3. Okay, so you know how to find out the determinants. 2 9 minus 1 minus plus it will be minus 3 minus 1 minus 1 plus 3. So it will be 2 into 8 plus it will be minus 4 minus 4. Okay, 16 minus 4 minus 4, it will be 8. Okay, so minimum number of spanning tree possible will be 8. Okay, so this is the correct answer, option A. Okay, got it? How we are solving the question? Is anyone facing problem to understand the concept? Can please unmute yourself and also tell me. Okay, so for your convenience I will repeat again how to find this one. Okay, so like for we have seen this graph. Okay, so if I take any other graph, okay, so let me take any other graph example. So this is a graph. Okay, so I am labeling the node like this, A B C D E. Okay, now what I will do, first I will be finding the adjacency matrix. So what will be this? First I will be finding the adjacency matrix. Okay, so please pay attention to this. So it will be A B C D E, A B C D E. This is the adjacency matrix. In adjacency matrix, all the diagonal element will be 0. Fine, no problem. And what will be other elements? If there is an edge between any node to any node, is there a edge between A to B? Yes, so A to B 1. Okay, otherwise is there a edge between A to C? No. A to C, there is no edge, so I will write down 0. A to D 1. Yes, A to D. Yes. A to E, there is no edge between A to E. You directly can't go. That's why 0. Fine, no problem. So like this, I'll write the rest of the thing. Okay. So this is the adjacency matrix. So whenever you have finished the adjacency matrix, it is fine. Now what you will do? Now I am writing in here. So what you replace all non-diagonals by -1. Okay, and what I will do? Replace all diagonal zeros by degree of corresponding vertices. Okay, then what I will get? So if I do this, what I will get from here to here? I'll get 2 so please pay attention that what I have done, replace all non-diagonal element by 1 if there is 1. Okay, so this was 1 here, so I have replaced it by -1. 0 will be the same. If there is a 0, it will be remain same. So -1 is replaced, 1 is replaced by -1 and 0 are same. Okay, then 1 is replaced by -1 and 1 is replaced by -1, 1 is replaced by -1 and 0 remains same. Okay, this I have done. And in the diagonal element, I have replaced it with degree of the vertex. So 2 is degree of vertex A is 2, degree of vertex B is 3. Okay, so that's right. So this is how. Then what you have to do? You have to find the cofactor of any element. Then what will be your third step? Find cofactor of any element. Okay, so if you find the cofactor of these two, so it will be basically the determinant. Okay, nothing else. So now comes question number 3. That given a weighted undirected graph, what will be the resultant spanning tree of Prim's algorithm? So till now what we have seen, that till now we have seen the what is the basically spanning tree. Okay, spanning tree means like this is the minimum number where we have minimum number of edges so that we can cover all the vertices. Okay, if it doesn't cover all the vertices, it will be like disconnected graph or multi-component graph. Okay, so we have seen the spanning tree, number of spanning tree possible of a fully connected graph. So this first question was our for fully connected graph. Then we have seen that if there is not a fully connected graph, then what is the minimum number of spanning tree possible. Okay, so if now you have a weighted graph. Okay, so these are the weights of every edges. Okay, these are the weights of every edge. Okay, so till now you have seen that there was no edge weights. So this there in this graph we have no edge weight, but in this Prim's algorithm we have edge weights. Okay, so now how what will be the minimum cost spanning tree? So in Prim's algorithm, what we find basically minimum cost spanning tree. So here basically why this algorithm, there is a need of this algorithm, like in a flood. So these are the villages. Okay, so in a flood, so all the roads are gone. Okay, now you have to, you are the you are a responsible person from the government of India. So now you have to make a bridge between each village. Then you know that from one village to if you want to connect from one village to other village, so this much time, this much days you require. Okay, to connect to from F to D you need 9 days. Okay, but there is a need to make the roads to connect the road as soon as possible. So that's why there is a need to find the spanning tree. Okay, which is basically minimum cost. In minimum number of days you can, in what will be the number of days, like minimum number of days in which you can develop the bridge so that you can connect each and every village. Okay, so this is the concept. Okay, now please try to solve this question using Prim's algorithm. So there is basically two algorithms, Prim's and kruskal. Okay, so these are, so what kind of graph this is? So this is a weighted graph and undirected graph. Also, if you specifically see, this is a edge weighted. Okay, and undirected. Okay, so what will be now? You have to find the resultant spanning tree for Prim's algorithm. So these are the options for you. So what will be the resultant spanning tree? So just follow the algorithm and find out the resultant spanning tree from this graph. So these are the options for you basically, A, B, C, D. So I'll be very happy, like I am also teaching you. So if you please try by yourself or maybe interact with me a little bit, maybe in chat also. So it will be very very satisfying for me. Otherwise it's like a one-way process basically. So this is your graph and you have to apply the Prim's algorithm on it. Okay, and find out the minimum cost. So in this kind of algorithm, like you don't have any source or destination. So you have to connect all the villages or all the vertices using, and from each so that you can reach each village, or you can you can give a tour to every village from starting from any village. Okay, so in the option, if you see that if you start from here, maybe this is a correct option for you. So if you start from node D, you can come here, then you can go to here, or maybe your wish is to go there to village C, then you can, if you start from here, then come here, then come here, then come here, then go to village C. Okay, so you can from, if you start from one node, you can reach every node. Okay, so how Prim's algorithm work to find this? So let me draw A, B, C, D, E, F, G. So this was our node A, B, C, D, E, F, G. Okay, so I have just written the vertices basically. Okay, now for Prim's algorithm, what you have to find? You have to find the minimum edge weight. Okay, like as I have told you that there is, so all the bridges are gone, all the bridge between the villages are gone. So what you have to find, you have to create a bridge from one node to another node. Okay, so what is the best possible thing you can do? So you can find out the minimum edge weight. Okay, is that, like, in one day you can make the bridge between B to D, in one day you can make a bridge between A to C. Okay, so just do the same. So you can start from this one also, or you can start from this one also, but both will take one day. Okay, so just start from any one of them. Okay, so I am starting from node B to D, like this. Okay, so this is a, in one day I can make the bridge. Okay, now what you have to do now, if you have connection from D to B, so you have started from here, from this bridge you have made first. So what you have to do, so you have to, for B and D, so you can reach to B and you can reach to D. So find out the all neighboring nodes of from B and from D. So you can see from B you can reach to E and G. Okay, from B you can reach to, E and G in 4 and 8 days. 4 and 8 days. E and G in 4 and 8 days. Okay, you can reach to E and G in 4 days and 8 days. Okay, from D you have nothing to, you have nowhere to go. So D is a dead end. Okay, so now what you have to do, so what you can do, choose the minimum one. So this is the minimum, in 4 days you can reach it. So just make the connection. Okay, got it? Now you have connection to E. Okay, you have connection to E. So as this is done, so I'll omit this, I'll erase this one. So now you have connection to E. Okay, so now see, from E, sorry, so from E you can reach to F, or you can reach to G. Okay, or you can reach to A. So from E you can reach to A, F, G. Anywhere else? I think no. A, F, G. Okay, A in 3, F in 2, and G in 6. A in 3. So you can, from E you can reach to A, F, G. Okay, A in 3, F in 2, A in 3, F in 2, and G in 6. 3, 2, 6. So now you have this much available data. So you can see the minimum one is this one. You can, from E you can reach to F in 2 days. So you will make a bridge there. Fine. Okay. Now, so are you getting my idea? Like, So basically what I am trying to do, I want to just show you the things that step by step only, like so. So this was our first step, and from here we have reached here in 2. Now if we again A, B, C, so this is done. So from G we have now what we have, we already has this one, like from B to D 1, okay, from E to B this was 4, so this was 2. Now what we have, now we have A to E, this one A to E is 3, A to E is 3. Like now we have explored the node F also. So if we have explored the node F, now see for in the neighborhood of F what we have. So in the neighborhood of F we have G, only D we have the new one, that is of cost 9, D with cost 9. So among them, so if we delete, so this is already done. If among this one, A is the less one, okay. So now A has also arrived. So if A is also arrived, so from A you can go to node C in 1. So A to node C in 1. So as this is done, you can delete this one. So now what is the minimum one? So C to 1, C in node 1 is the minimum one. So you can go to A to C in 1. Okay. So now C is also arrived. So from C, what you can do? C, you can go to D at 4. Okay. So there is of no use. Okay. Okay. So this is done. Okay. Now what you have left? So you have left node number G, B to G, okay, B to G. Okay. Now you have node number B to G. Okay. So this is left. So from here. So this is, you can reach in 6 days. Okay. So this will be your E2G. So I have made a mistake. So it is basically E2G. This one E2G you can reach in 6 days. So this will be the answer for your question. Okay. Fine. So option A. This. So you can check that what we have made and what we have the option. Option A is correct one. So I think we have made it correctly. Okay. So in exam what will come, basically in GATE exam also it comes that you have given a graph like this and you have to find the minimum cost spanning tree, or they will tell you find out the cost of the spanning tree. So if the question is about to find out the cost of spanning tree, then you have to just add the numbers, like add 6, 2, 4, 3, 1, 1. So this will be, so 8 plus 4 12, 12 plus 3 15, 116 and 117. So 17 is the minimum cost. Okay, so this is the cost of spanning tree. Okay, So now there is another problem. So this is the given graph. So now what would be the resulted spanning tree of using kruskal algorithm? So you have to use the kruskal algorithm to find the minimum cost spanning tree. So these are the answers. So please try by yourself first. Thank you, Vishaka, for your response. So, so if anyone has any problem to solve this question, like if you can understand how to solve this one, you can just write in chat or like unmute yourself and tell me. Okay, there is no problem. Like this is some complicated, some like little things you have to understand. So if you are not getting the things, just unmute yourself and tell me like where there is a problem. Yes, no problem, Mishaka. So I am telling you that what are the Prim's and Kruskal algorithm. Okay, so Prim's and Kruskal is finding the minimum cost spanning tree. Okay, so minimum cost spanning tree means you have to connect all the nodes. Okay, with like so that so there are many edges. Okay, many edges are there. Okay, so you don't need all notes. Okay, just listen my story only. Like maybe uh, you are a person. Okay, you are from government official. So first, so if this is the case, if the graph is given like this, okay, so you assume these all are villages. These all nodes are villages. Okay, and in tsunami or flood, all the bridges are gone. Okay, so no, or these are island basically. Okay, so no island can contact to any other island. Okay, so you are from government of India, so you have to make bridges between this island. Okay, so this is the case basically. So if you draw like this, okay, so what was the case? So this was H I G C F A B D E. So this is the island. Okay, so I have just drawn this graph. Only the nodes only. You see H I G C F. So I have just drawn the islands H I G C F. Okay, any problem? So this is very easy. Like there is no ambiguity in this. Like only I have drawn the edges. Vertices. So you think as a island, and all bridges are gone. Okay, now what you have to do? So you have to construct a bridge between the islands, so that from any island you can go to each other islands. Okay, so here in Prim's algorithm you can see that your map is given like this. So this is your Google map. So this is your island map basically. Okay, so island map is given like this. Okay, so before tsunami there was multiple bridges. Okay, like from sea there was a bridge. So if you want to reach from B to G, you can reach by this bridge. Okay, but this was the correct spanning tree. We found out this is the minimum cost spanning tree. So you can see that from to reach B to G using this bridge you need 8 days. Okay, but if you see, like if you reach from here, okay, so you can also reach G. Okay, so this age weight, so these are called age weight. Okay, 8, 4, 6. So this age weight tells us that if I want to make a bridge between these two villages B to E, how how many days I need. Okay, so I have to do my work. I have to make a bridge between all the island as soon as possible. Okay, so that's why to develop the bridges between all the islands, I will run some algorithm. So what will be my algorithm? So first I will find. So there are two algorithms to find this minimum cost spanning tree. Okay, in two ways you can find it. Okay, so one is called Prim's algorithm and one is called kruskal algorithm. So these two are basically scientists. They found out this algorithm. Okay, so here in Prim's algorithm, it says that find out the minimum age first. Okay, so minimum age with minimum age weight. Okay, so minimum age mean minimum age with minimum age weight. Okay, so these two are the ages with minimum ages, that is 1. Okay, I think there is no problem. This is very simple. You can see that this is only 1 and other node, these two are only 1. So these two are minimum age weight. Okay, now whenever you find a minimum age weight, then connect it. Okay, so you can see here that I have connected this one first. Okay, this one. Then what you will do, you will find the neighboring node. So in your village, in your country, basically these two islands are connected now. Okay, so now see from island B which other island you can go in minimum cost, and from island D which other island you can go in minimum cost. So you can see from D you can go to F in cost 9. Okay, but from B you can go to E in cost 4, or assume like this, that you can make a bridge from B to E in 4 days and from B to G in 8 days. So choose the minimum number of days. So now from B you have, and B and D you can reach. So from B and D you have to make the future plan. To make the future plan, you can reach to E, G and F. To reach E, G and F, you need 4 days, 8 days or 9 days. So which island you want to go? So you will choose the minimum one. So you can see that in 4 days I can reach to E. So that's why I have done. In 4 days I can reach to E. Okay. Then so you have a connection. Now you have a connection to this node. Okay. Now you see that from E you can reach to A, F, G. So to reach A it is 3, to reach F it is 2, and to reach G it is 6. Fine. So now you can go to F in 2 days. So choose this one. So this is like a greedy algorithm. So you are very greedy. You want to go each island in minimum number of days, so that as tsunami came, this island has no food. So you have to reach as soon as possible. So you will choose the minimum cost part. Okay. So this is the thing. Okay. So from F you will choose the, from A, E, F. So you will choose the minimum one. So as from now you have the option to, from E you can reach F. Now you can see that, so this is the minimum one, you can go to A. So this is the minimum one, as it is 1. Okay, so like this. So I think you got the point, that how Prim's algorithm is at least working. So now we will discuss that how kruskal algorithm is working. Okay. So in kruskal algorithm, it says that same thing, like you. So these are the islands. Now what you will do, so what it will do, what you will do, like you will choose from this graph. So you will choose the edge with least cost. So you can see the least cost is 1, this 1 and 1. So these are the least cost. Okay, so you will add this node H and G with cost 1. And what are the least cost? Now in Prim's what we did, that we have access in Prim's, this is the kruskal algorithm, but in Prim's what is the difference, that I am telling only. In Prim's you have access to these two islands. Now from these two islands you saw that what other island you can go. Okay, so this was the Prim's algorithm. Okay, but in kruskal what you do, that you just choose the edges with the minimum, which has the minimum weight. Okay, so you can see this 1 and 1, these are the minimum weights. So make make the bridge between these two villages. Then choose that. So 1 is done, 1 is done. Then see that minimum edge weight is 2 and 2, these two. So you now you will build these two villages. Okay. So now I have seen that what are the, so 1 is done. Okay, so this, so in Prim's algorithm what you have to do, start the edge with least cost. Okay, now find out the second least edge, so that is 2. Okay, in Prim's we will get a tree, but in kruskal we can found a forest. Okay, so next what is do, what is सर रात में कुछ बन रहा है तो मुझे भी इंक्लूड कर लेना. तुम लोग आना, मैं जा रहा हूँ, मेरे काम वाली आ रही होगी. So so add these edges, because this edge with cost 2 are the least weight. Okay, fine. So now 1 and 2 is done. Okay, so this was the least weight edges. Okay, this is done. Now 3 is there. Okay, so add these two also. So there was three edges with uh, weight 3, but you can see that this C is already connected with B. Okay, this C is already connected with B using this edge. Okay, so that's why I will not make this edge. Okay, so I will not connect this edge. Okay, got it? Because C is already connected to B. Okay, okay, so now what we have, so we have utilized C. So now 4. Okay, so now we see that if we need to include 4 or not. We can see that the 4 need not to be included because it is already there here basically. So here it is already, and already this H and I has a connection somehow. Okay, they are already connected, so I will not use this. Then what comes? Then it will come 6. Now what comes? Now this 6 is okay. Now and this one. Okay, because you can see here this is 10 and this is 8. So you connect using this 6 from here to here. Okay, and this is 9 is remaining. So what will be the correct answer? So correct answer is option C. Okay, now check once that what we have did is right or no. Okay, so here what I did basically, if I write in a short, like okay, so here basically always find out the edge with minimum weight. Okay, so here you have to always find out the edge with minimum weight. Okay, but in kruskal what you did, so you find out the edge weight with minimum weight for the first time, but in second time you find out the edge weights adjacent or neighboring to the connected nodes basically. So first you find out that least edge weights what 1, okay, and B and D are the connected nodes. Then you find out their neighbors. So these are the difference. So I think you understood the difference between Prim and kruskal and how to find out the minimum cost spanning tree. So if anyone has any problem using this, so Vishaka told me that sir, but this is not minimum weight now, it's only about connecting all the vertices. Yes, it is connecting all the vertices and it is minimum also. So Vishaka, you can see that if you see the options also, if you see the options, other options which are not which are not correct, you can see that this C is only the minimum cost. This C has only the minimum cost. Okay, to connect from each node to other node. Okay, you can find out, just you can add any other thing, any other combination, and you can see that maybe it might be same or greater than cost of this graph. Okay, so this is the minimum only, because you see that always we are choosing the minimum edge weight. Okay, always first we have choose this one. Okay, we have choose this one. Okay, always we are choosing the minimum edge weight. Okay, first we choose this one, then we choose this one, then we choose this one, then this one. Okay, then we choose edge weight with 3. Okay, Then we also had a edge here. Oh, sorry, we also had a edge here, as stated here. Okay, as stated here. But already this I and C is connected. This I and C is already connected. Okay, so if you start from I, you can come here to here, or here to here to here. Okay, so you can go to from I to C in any way. So you don't have to you don't need to add this edge with minimum cost 3. Okay, so this is the thing. Okay, then you add this one. Okay, so this is cost 6. Then you find out the minimum cost. This is cost 9. So like if you add this one, okay, so these two are already connected, F and D, so you don't need to connect this one. Okay, so this is how the things are done. Okay, so I think this is, but then sir, weight in I to C is more than 3. Weight in I to C, from I to C. No. So so from you here, you don't have to add weight like this. So you are basically calculating from I to C, reaching from I to C. You are calculating like 2 plus 1 plus 3 plus 2. So you are calculating like this only. But for Prim's algorithm, this is not the case. Okay, so from so this should be the minimum cost spanning tree. Okay, so so basically here you have to make the bridge first. Okay, you don't have to reach from source to destination. So there are other algorithm like dijkstra and bellman 4. In this algorithm you will have source and destination. There you have to reach from one source to one destination. There you will add the edge weights. Okay, here you just have to make the bridge between every vertices. Okay, so this is the thing. So I think this is clear. Now next question is, so this question is GBA undirected graph, GBN undirected connected graph. Okay, with distinct edge weight. Let Emax be the edge with maximum weight and Emin the edge with minimum edge weight. Which of the following statement is true? Okay, so this is the question. So please read the question and try to answer it in the chat box. Please read the question. So this is a very simple question. So Emax is the edge with maximum weight and Emin is the edge with minimum weight. So here it is saying that in option A, every minimum spanning tree of G must contain Emin. So as Vishaka's doubt is regarding this only. Okay, so please read the question and try to understand from your heart only, like then you will understand this. So see this graph. Okay, so this is a graph. So you have to find the minimum spanning tree here. So the question is, every minimum spanning tree of G must contain Emin. Okay, so Emin is, so this is the Emin because this has minimum weight, and this is basically E max. Fine. Okay, so this is E min and this is E max. Okay, so now what you have to do? So uh, in Prim's algorithm also, first we find the edge with minimum weight, and in kruskal algorithm also we have seen that we find the edge with minimum weight. Okay, so this is, of course, this is very true that every minimum spanning tree of G must contain the E min. Okay, so so if we follow the kruskal algorithm to build the spanning tree, what we will do, we will find the minimum edge with minimum edge weight. Okay, then we will check its neighbor A B. Okay, then from A B we can see that from B to C we can reach in weight 2. Okay, so we'll connect the edge. Okay, now we have access to C. Okay, so so Prim's algorithm state that from A, B and C you can reach D in weight 3. Okay, so if you follow the kruskal algorithm also, kruskal algorithm says that first find the minimum edge weight 1. If it is done, then find the next minimum edge weight, which is 2, then make the edges, and then find the next minimum edge weight, that is 3. This is 3, this is done. Okay, then you can see that E is not connected. Okay, so E is not connected to any node. Okay, then what you have to do, so here the edge weight is 4, but here the edge weight is 100. Okay, but E is not connected to the island. Okay, so you must have to add this one. Okay, to connect E to A. Okay, so the thing is, if Emax, so this is the Emax, if Emax is in a minimum spanning tree, then its removal must disconnect it D. Okay, so this is the case. So if you remove this, so this is Emax, this is in the spanning tree. If you remove this one, your graph will be disconnected. So this is also true. Okay, so no minimum spanning tree contains Emax. So you can see here that this was the minimum spanning tree, but it contains the Emax. Okay, and because you don't have any other options to choose. Okay, any other alternative you have. Okay, and G has a unique minimum spanning tree, so always the graph will have a unique minimum spanning tree. Okay, so what our question was, so our question was to find the false statement. So this is the false statement, that no minimum spanning tree contains Emax. Okay, done. So now the next question, that is, which one of the following cannot be sequence of edge added in that order to minimum spanning tree? So I have shown you how to solve the question. So please try to solve this question and write the answer in the chat box. बताओ क्या हुआ आज, कुछ हुआ?
हाँ सर, वो जो अपने जो ऑटो इनपुटर का वो जो बोला था ना, वो उसके खुद के ही वैल्यू से कंपेयर कर रहा है। ऐसे कोई ग्रुपिंग वगैरह का क्वेश्चन नहीं है, वो एरर निकाल रहा है खुद के ही वैल्यू से।
उसका कोड किया क्या?
उसका कोड सर दिया हुआ है, उस पर मतलब जो लिंक था ना उस पर दिया हुआ है उसका कोड देखा मैंने, तो वैसे ही किया हुआ है।
अच्छा, तो कल मैं वो अच्छे से समझूंगा तुमसे।
हाँ,
और क्या है, मतलब वो वाला पेपर समझ गए हो ना जो?
हाँ सर, पेपर मतलब पढ़ लिया था। और
हाँ, और हाउ यू आर फाइंडिंग दी वॉल्यूम ऑफ द स्टॉक एंड ऑल?
हाँ सर, वो वॉल्यूम ऑफ द स्टॉक वो देख लिया था। वो रेशियो निकाल रहे हैं, उस रेशियो के बेसिस पे एक पैरामीटर मान लिए कि एल मैक्सिमम इतना होगा, और फिर उससे रेशियो निकाल रहे हैं, रेशियो को उससे मल्टीप्लाई करके वॉल्यूम निकाल रहे हैं उसका।
समझ गए हो ना वो चीज़? तो वो मुझे कल सुबह आके बताना, ठीक है? कल थोड़ा सुबह कल, ठीक है, तुम आना। पर कल वो चीज़ मैं पूछूंगा अच्छे से अंदर से।
हाँ सर, वॉल्यूम वाला और इनकोडर वाला।
हाँ, वॉल्यूम वाला और इनकोडर, मतलब जिसमें वॉल्यूम फाइंड कर रहा है और अपना बाई होल्ड एंड सेल फाइंड कर रहा है बेसिकली।
क्या सर?
बाई होल्ड एंड सेलिंग सिग्नल। So these are the given edge weights. Okay, given ways to solve the kruskal algorithm. Okay, So now you have to find the which should cannot be the sequence of edges added. So in many ways you can add your edges. Okay. So you can see here that in kruskal algorithm what we find, that we first find the minimum edge weight. So this one is the minimum edge weight. So AC, okay, this is fine. I can add CE, okay, CE I can add, AC I can add, CE I can add, CE I can add. Now then CE, then I can add CE, then EF I also can add, because EF is will minimum edge weight, AC, EF. Up to this is fine. Now EF, EF, AC, this is fine. But can you in third step, can you add EC? EC, EC is okay. You can add EC is one. Okay, EC is one. You can add. Okay. So okay, fine. Now in fourth step, so all edges with edge weight one you have completed adding. Okay. So all edge with edge weight 1 you have completed adding. So now what you can do, so now you have to find the next minimum edge weight, which is 2. Okay, now you have to add these edges. So eb is fine, you can add. fb is 2, you can add. bd, so bd is of edge weight 3, and fd fd you can add. Okay, so this one. So here it is a problem. In step 4 you cannot add bd. Okay, because already in already bf is remaining. So if you try to add the add in this stage, so what you can do, a c d b e f. So this is your island. Okay, now you have to add. So you can add c. I am adding in this sequence c. Okay, in 1. Now ac in 1, then ef 1, then bd. So you have option, you already have option, you can add bf in 2 or df in 2. Why you should add df in 3? Because already you would have option to add this bf in 2 or df in 2. Okay, or be in 2. So why you are not doing this thing and you are adding db? So that's why this sequence is not possible. Okay, yeah, because you have given the right answer, and Vishaka, I think you have got that why your answer is incorrect. Okay. Okay, now our question is, which one of the following cannot be sequence of edge added in that order to a minimum spanning tree using Prim's algorithm? Assume that the algorithm start either at vertex B or F. So here there is a simple assumption only. So as there is so in Prim's algorithm, like you have to find the sequence, that which sequence is not possible. Okay, and find out the sequence. Okay, so in Prim's algorithm what we do, we found out the minimum edge weight, which is the 1. Okay, okay, so that is bd you can add, or fe you can add. Okay, fine, these all are fine. Now please try yourself and tell me the answer using the Prim's algorithm. So if anyone solve this question, please write the answer in the chat box. Option B. Okay. So, if we see in the answer, like BD, if we connect BD first, okay, we connect BD first to edge weight 1. Now we have two options like from BF and BA. If you connect BD first, so you have these two options A and B. Now you can connect BF and BA. Okay, BF BF you can go to 2 in 2 days, and from B to A you can go to A in 2 days. So when I solve the question, so I see these vertices as an island, and I in my mind the calculation goes like this, that from B to A I go in 2 days, from B to F I can go in 2 days. Okay, so then this two is right. Okay, now I have access to island A, B, D, and F. Fine. Now FE and BF, is it possible? FE. So FE. So okay, yes, it is possible because it is of edge weight 1, and BF and BF. BF, yes, BF was there only. Yes, was there. And AB is possible. BF is also possible. Okay, fine. This is fine. Now, CE, is CE possible? Yes, because I have access to E, and I can reach with 2. Okay, and FE, yes, FE is possible because okay. Okay, basically these are basically two graphs, two different graphs basically. So this FE is also possible. Okay. Now, no, I think we can check in different way. Like one by one we can check. Okay. So we have to go one by one. Okay. So first we'll go with option A. Okay. BD, one fine. BF, BF, yes, we can go within H2. Okay. Now FE, yes, FE is 1, fine. Now CE, CE is 2, fine. Now BA, BA is 2, fine. So all the vertices are connected. So option A is correct. Okay. So we can reach the option using the Prim's algorithm. Option A is correct. Okay, this sequence is correct. Okay, so now using option B. Now using option B. Okay, BD, yes, BA, yes, BF, BF, yes. Now FE, yes, and EC. So this is also correct. Okay, so this is also correct. Now if we check option C, if we check option C, FE, correct, because it is minimum edge weight. Okay, now FB, correct. Okay, BD, correct. Okay, now AB, correct. Now EC, correct. Okay, fine. So this is also correct. Okay, now check with option D. Okay, so option D says FE, EC, then BD. So you can see using Prim's algorithm you can't do this. You can't make a edge here now because you have access to go to these three island only. Okay, so if you want to make a connection you have to you can make this connection. Okay, but you can't directly make B to connect B to D because this because B and D has no neighborhood with E, F and C. Got it? So this is your answer, that this sequence will not be possible. Okay, so I think you understood the approach basically. Okay, so any problem? So I hope you understood that how we are solving this one. Okay, so also one thing that this 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 graph, if I connect using this edge between B to D, so it will basically a forest. Okay, because this is a tree and this is a tree, so forest is not possible using kruskal. So forest is possible using kruskal only, but using prims you can uh, प्रकाश प्रकाश धीरे धीरे, so this is not possible. So what is the best case time complexity of kruskal algorithm? So I am directly going to the algorithm. Okay, and will let you know that how this is possible, that what is the time complexity of the algorithm, because if I make you understand the algorithm and all and the implementation details, so you don't know about the heaps and all. I think in coming week you will be aware about the heaps and all. So basically there is a thing called heap which is called mean heap. So in mean heap this is a tree kind of structure. So like where every time, so the root element of the tree will be the minimum. Okay, so this is called the mean heap. So what is the max heap? So if root of the tree is maximum, so that will be max heap. So using the all edge weights, so you have to find the minimum one. Okay, in Prim's kruskal algorithm, so here you have to find the kruskal algorithm. So in kruskal algorithm you always have to find the edge with minimum edge weight. Okay, and just add the nodes between the minimum edge weight. Okay, so creating the mean heap. So so you will create a mean heap of the edge weights. So it will take order of mean heap takes order of n. So as there are e number of edges, so I have written that creating mean heap will take order of e. Now delete minimum from mean heap and add to MST if no cycle form until v minus 1 edges are added to MST, and delete min takes order of log e base 2. Okay, so basically, so whenever you you have mean heap, so this is the minimum element, so you will delete this element because you have already added the or connected the bridge between these two nodes using this edge. Okay, that edge weight, so you will delete this one and add to the minimum spanning tree. Okay, MST means minimum spanning tree, and if no cycle formed until v minus 1 edges. Okay, so deleting takes log n times or log e base 2. Okay, now best case is when minimum spanning tree is formed by first v minus 1 delete means without getting a cycle at all. Okay, So that's why we have found using this calculation that best case is E plus V log P. E for creating mean heap, and for V minus 1 is we are getting V log P, V log E. Okay. Now time complexity of Prim's algorithm. Okay, using binary mean heap. So you can find out that for using binary mean heap, build mean heap produces order of V. Okay, because for for Prim's algorithm, you have to go node wise. Okay, in kruskal you have to go edge wise. Okay, so this is the time complexity, that is V plus E log P. Okay, this one. Okay, now the question is, let T and T dash be two spanning trees of a connected graph. Okay, suppose that an edge E, ओ सर थोड़ा धीरे बोलो, मैं धीरे बोलूँ. So let T and T dash be two spanning trees of a connected graph G. So suppose that an edge E is in T but not in T dash, and edge E dash in T but not in T. The remaining edges are assumed to be same. Then which of the following is true after performing the following operation? So these are two operations. Okay. Now please try to solve this question by taking some examples. So maybe this is a graph. Okay. So this is a okay, so this is a spanning tree of graph G. Okay, and this is a spanning tree of this T dash. So both are spanning tree of graph G. Okay, so maybe this was a graph. So you can see that this is a possible spanning tree, and this is a possible spanning tree. Okay, fine. So the question is, an edge E is in T but not in T dash. So this edge, yeah. T dash, and or maybe you can say and edge E dash in T dash but not in T. So it is saying that, so what one is saying? So one is saying that T minus E union E dash. Okay. So it is saying basically so now this is the answer. Right. Now if E is deleted from T and E dash is added, then the resultant spanning tree is indeed T dash. So what is he saying? That delete E from T, delete E from T. Okay, and
that's right. No, but you can
and
share.
E dash is added, then E dash is added.
You can send me the link.
Then the resultant spanning tree is basically the T. Okay.
Okay. You can send me the link.
So after this operation, the both are spanning trees. Now which of the following are true about minimum spanning
Now
tree?
I'm working without taking the premium version. Actually, I face very big problem.
So option D is correct. For a given graph, more than one MST is possible. MST means minimum spanning tree.
Per month. So I'm also waiting. Friends are 80.
And for a given graph, if there are more than one MST, then at least one of the edge weight will be repeated. Yes. So this is true from this one, like at least one edge will be repeated. Okay. If the given graph is connected and no edge weight is repeated, then exactly one MST is possible. Okay. So this is also true. If the given graph is connected and no edge weight is repeated, okay, then exactly one MST is possible. Okay. Like for this graph you can see, like for this one, like here only one MST is possible because no edge weight was repeated. Okay, like 1 2 3 4. Okay, and only one minimum spanning tree is possible because no edge weights were repeated. Okay, and fourth option is there will be no minimum spanning tree if graph is disconnected. Okay, so if there will be no spanning tree, graph is disconnected. So disconnected graph means basically this one. So these are disconnected graph. So no minimum spanning tree is possible. Okay. So now assume dijkstra algorithm to find out the shortest path from node A to the in following graph. Okay. So you have to use the dijkstra algorithm. Okay. Now as we have a very short time, so I'll show that how dijkstra algorithm works basically. So there are two algorithms. One is called dijkstra, and bellman code. Okay. Okay. So in dijkstra, so it for these two algorithm is the graph can be undirected or it can be directed. Got it? So this is an undirected graph. Okay. In next question you might be getting a, so this is a directed graph where you have to run the dijkstra algorithm. Okay. So this is an undirected graph. Here you have to run the dijkstra algorithm. So dijkstra algorithm can work both on undirected graphs and undirected graphs. But the problem is if there is a negative edge weight cycle, okay, or if there is a cycle, then dijkstra algorithm can't detect it. Okay, so I'll tell you that what is a negative edge weight cycle. But if there is a negative edge weight cycle, bellman code algorithm can detect it. Okay, so now I'll give you an example. So this is a negative. So this is a graph. Okay. Now, what bellman for dijkstra algorithm? What you will do? Then, what is your source node? So your source node is A. So you will always be given the source node. Okay. So your source node is A. Okay. So from A, first it will be infinity. So to reach B, first it will be infinity. Okay. Now so from A in to reach B, you so there is a concept called relaxing an edge. Okay. So relaxing an edge basically means like basically relaxing an edge. Relaxing an edge basically means that you explore the edge. Okay. So maybe you can find a good path. Okay. So basically if these are two nodes. So maybe this is 1, this is 5, and this is 2. Okay, so now the relaxing an edge means, so you explore both the path. Okay, so if you explore this path, so to reach B from A, you need 1 unit of time, you need 5 unit of time. Okay, but if you explore, you have not relaxed this edge from B to C. So if you have relaxed this edge, you can see from A you can reach to C in 3 hours, but you are now, but previously you were reaching from A to C in 5 hours. So as Vishaka was telling, was calculating from the edge weights. So here you have source A, always you have source A, and you are relaxing the roads basically. Okay, you are exploring all roads. So if you explore all roads, you can see that from here, so in 3 hours you can reach from A to C. But if you go directly from A to C, it will take 5 hours. Okay, so this is called relaxing edge. Okay, so what you have to do now, from A, all you have infinity distance. Okay, now what you will do, from A to B you can reach in 10 hours, from A to C you can also reach in 5 hours. Okay, so what is the minimum one? 5. Okay, so this one, A to C is fixed. So from A to C you can reach in 5 hours. Okay, now again what you can do, so from C, what you will do, from C, if you are coming from C, so infinity minus 8 is infinity. Okay, now what you can do, from C to, if you can you reach any other, like from C to B, where you can reach. So always you have to go like A, C, then B. Okay, you don't have any other option. Okay, this is how dijkstra algorithm works. Okay, now what is Bellman-Ford algorithm? So Bellman-Ford algorithm says that relax relax the nodes, or relax the edges, relax edges v minus 1 times, like relax all edges v minus 1 time. Like how many nodes are there? There are 3 nodes. And how many edges are there? There are three edges and 3 nodes. So how many times you will relax them? So you will relax 3 minus 1, that is 2 times. Okay, so this was your given graph. Okay, so if this was your given graph and you relax 1 time, what you will get? So from A you can reach to B in 10. Okay, now from C you can reach in 5. Okay, fine. So this is your, and this was edge, but this was not relaxed. Okay, so if you relax again, what you will get? You will get, so you can see that so this one is, from this state, so 10, so this is fixed, 10 minus 8, 5. Okay, so so if you relax this is, so this is 0 basically, so 0 plus 10 is 10. Now here we have 5, but if we do 10 minus 8 you can get 2. So previously it was 5, but 5 will delete and you will get 2. Okay, so 5 hours is more, 2 hours is less. So how many times you are relaxing? You are relaxing 2 times. Okay, because b minus 1 time you have to relax. Okay, so this is the case. I think got it. So this is the process of Bellman-Ford. Okay, so in Bellman-Ford you can basically get the negative edge cycle. So to get the negative edge cycle, what, like if you, what we can do, Now this is the assume this is the dijkstra algorithm to find the shortest path from node A in the following algorithm. So shortest path from node A.
हैप्पी बर्थडे बोल रहे हैं, कह रहे उस दिन मेरा मन हुआ आपको हैप्पी बर्थडे बोलने आऊँ मैं, बट मेरे को लगा कुछ और चल रहा है तो फिर मैं नहीं आया। मैंने कहा मेरा बर्थडे नहीं था, आज का बर्थडे था। हेलमेट का हेलमेट तो नहीं है, ये हेलमेट दो और एक दो मैं पता जाएगा ऊपर।
जा रहे हो क्या तुम लोग?
कल को बोल ही रहे, कल करना है, आप तो बोल दो, ये लोग माने कहाँ हैं? ये कल गाड़ी से चलेंगे कहीं।
हाँ
लास्ट डे है ना अपनी उसका, वो पढ़ा रहे हैं, ठीक है।
अरे बोलो बोलो।
फ्रीडम का लास्ट डे, बोलो ना ठीक से बोलो ना।
So this is the thing that from A you could have reached to E, M, G or T. So all are first infinity. Okay. So like here you can also draw it here also. Like now see, from E you can reach in 7, from G you can reach in 2, from here you can reach in 6. Okay, here you can reach T. Okay, in one go you can reach here. So that is E it is 7, okay, M it is 6 and G it is 2 and this is infinity. Okay, so now so after this you will relax A G, okay, A then G. Okay, now from okay this is added, so in your shortest path it is added that from A to G it is fixed. Okay, now after G where you can go, now you can see that you can reach T to 3 plus 2 it is 5. Okay, also you could have reached from it is 7, yeah. Okay, also you could have reached from 7 plus 4 11, but you can see that 3 plus 2 is lesser than 11, so it is 5. Okay, so T from G to T, from T it is 5. Okay, all are remain same. Okay, so here you are adding A G T. Okay, fine. Now you can see that G is the minimum one. Okay, now if you relax again, now see here you have reached 5. Now you can see like to reach E from A it is 7, to reach M from T, to reach M from T. Okay, do you need any less time? 5 plus 4 9, 5 plus 2 7, and from G it is 7. No, there is no less time, but from to reach G you need 7 times. Okay, so this is the case, like A G T, then you can sorry A G T M. Okay, you can, so this is your shortest path, but now you have to find the number of edges not included in any of the shortest path from G. So you can see that T M M E, like this one, T M M E, okay, M A A E, M A, okay, A E. So these are not included in the shortest path. Okay, so this the solution is. Now question 12 is which of the following standard algorithm is not a greedy algorithm? So greedy means, so you are already always looking for the best option. So Bellman Ford shortest path algorithm is not a greedy algorithm. Now, so this is also a question of dijkstra. Okay. So the question is about the question is about like how you will solve this. Okay. So first you know that all are infinity. Fine, no problem here. Now you can reach q to 1 in one go, that to add 1. Fine, no problem. Okay. Okay, from here you can also reach in 6. Okay, so each iteration I am using, I'll try to use the different color. Okay, in second iteration what you will do, so now you can reach here with 2. Okay, so previously it was infinity. Now you can reach in second relaxation, you can reach it in 2, and in second relaxation you can reach it in 3. Fine, so all are done. 1 1 2 3, all are done. So if you start from P, what is the order in which the shortest path are find out? So order is basically from P you go to Q or you go to T. Okay, then you go to so you can go both way, P then Q and then T. Okay, so as you can see in option it is given Q, so I am not exploring this option. So PQ. Okay, then what, then R. Okay, then I am going here to here. Then what I am doing, that I am going this way. If I am going this way, PQ1, then 2 plus 1 3. Okay, then U. Then what I am doing, then I am then starting from T. Okay, then also I can start from here also, like, so this one is also in third iteration, like, so in third iteration it will go to, so this is 2, and from 2 to 4. Okay, so PQRUS T. Okay, so PQRUS T. This will be the option. Okay, so blue one is the first relaxation, red one is the second relaxation, and yellow one is the third or fourth relaxation. So now question is, we are given a directed graph. Okay, directed graph represented as an adjacency list. Okay, in which each vertex has at least one incoming edge. Okay, this is the adjacency list. Okay, these are the adjacency list. Okay, and we would like to print out for each incoming edge and one outgoing edge. We would like to print out for each vertex j the list of vertices pointing into j. What is the most accurate description of the complexity of the computing these quantities in terms of n? The number of vertices and m is the number of edges. Okay, so this is the question. So the directed graph is given. Okay, so this may be the directed graph. Okay, so this one. Okay, now so in adjacency list it is given in which each vertex has at least one incoming edge and one outgoing edge. Okay, so maybe it all has at least one incoming edge and one outgoing edge. Okay, so this all has incoming edge and outgoing edge. We would like to print out for each vertex j the list of vertices pointing into j, and what is the most accurate description of the complexity of the computing these quantities in terms of n. So in one pass of the original adjacency list, we can build as new set of list where we associate for each vertex the set of neighbors. Okay, and in basically in one pass of the original adjacency list, we can build a new set of list where we associate with each vertex the set of neighbors with edges pointing out into the vertex. This can be done in order of m time. If we allowed allowed disconnected vertices, it could be that m is 0, in which case we would have to declare that time be order of n plus n, since we need order of n time to set up the list. Okay. Now the second question is, consider the following strategy to convert a undirected graph with negative edge weight to one that does not have negative edge weights. Okay, so you have a consider the following strategy to convert an undirected graph, okay, with negative edge weight to one that doesn't have negative edge weights. Okay, so basically if a graph has negative edge weight, you have to convert the graph so that the negative edge weight is gone. So basically in Bellman Ford, we can find out the negative edge weight. Okay, so the maximum, let the maximum magnitude negative edge weight in the graph is the minus k. Then for each edge in graph with weight w, update the weight to w k plus 1, w plus k plus 1. Consider the following claim. To solve the shortest path problem in the original graph, we can run dijkstra algorithm on the notified graph and subtract the added weight to get the original distance. Okay, so basically this adding an weight to each edge increases the weight of path proportional to the number of edges. Okay, so long shortest paths get penalized. In a tree, or tree means basically a connected acyclic graph, there is only one path between any pair of nodes, so the shortest path is invariant. So the right answer is, the claim is true for all graphs. Now consider the following algorithm on a connected graph with edge weights. Edge weights are like this: sort the edges as e1, e2, em in decreasing order of cost. Okay, so e1 is with highest cost. So start with the original graph. Consider each edge ej if the edge is part of a cycle and then delete it. Now which of them is not true? So in kruskal algorithm, we find out the each edge with minimum weight. So here they are finding out the edge with maximum weight basically. So if the edge is a part of a cycle, then delete it. Okay, so this is the reverse version of kruskal algorithm. Any edge that is a part of a cycle can be deleted without disconnecting the graph, because it is a cycle. Because if this is a cycle, then if you just only omit one edge, so the graph will not be disconnected. In the end we get a minimum cost spanning tree which has exactly n minus 1 edges. So at most n minus 1 edges will be deleted. Okay. Okay. Now the question is, consider the following strategy to solve single source shortest path problem with edge weights from source S. Replace the each edge weight w by w edges of weight 1. Connect by new intermediate node. Run breadth-first search to modify the graph. Find the shortest path to each of the following original vertices in the graph. Now which statement is correct? The strategy is sound, but the size of the graph will be proportional to the edge weight in the original graph. So the complexity will increase very much. So the strategy will solve the problem correctly, but is not as efficient as dijkstra algorithm. Okay. Now the question is basically, suppose we have a graph with negative edge weights. We take largest magnitude negative edge weight minus k and reset each edge with w to wk plus 1, which of the following is true. So the ascending order of the edge weights is unchanged if each edge weight is increased by k plus 1. So Kruskal's algorithm runs in exactly same way as before and produces the same tree. In general, since every spanning tree has exactly n minus 1 edges, so the increase in weight uniformly affects all spanning trees, so that minimum cost spanning trees are unchanged. Prim's algorithm is not affected by negative weights. Okay, so this question I prepared for today. So I think you have understood the concept of Prim's and Kruskal and Bellman code and dijkstra algorithm. So you will be able to solve the question easily. So thank you for attending the session. So I wish you all a very good day. Okay. Uh, Thank you so much. Thank you so much for participating. Sir, will you share this PDF? Okay, okay. So you want this PDF from me? Okay, okay. Just I can share this in this chat only.